Good day, class. In this discussion, we will discuss the practical applications of integral calculus. The first application would be regarding the areas of plane regions. In the past, we have discussed the area of plane region such that the region is bounded by a curve and the x-axis. However, in this particular discussion, we will expound on that particular topic by considering a region bounded by multiple curves. Now, recall from our discussion in the past that the area under the curve, as shown in the figure, is can be calculated as the integral of f of x dx from the lower limit x is equal to a and the upper limit x equals b. So that would be the area of this region. Now let's try to discuss why this is the formula for the area. Consider rectangular strips that would cover this particular region. So this is called the area by approximation, wherein we just calculate for the area of each of these rectangular elements and we just add the area up, and that would be approximately the total area bounded by the curves or the area of the region. However, it is noticeable that there are some areas that were not considered in the region. Thus, the approximated area is not that accurate. So, how can we make this more accurate? Now, consider the width of this particular rectangular element represented by the points x1 and x2. So therefore, the width will be equivalent to the difference of the coordinates of these 2 points. So x2 minus x1. Now, notice what happens if that particular width of rectangles becomes smaller. As we consider smaller width, as we can see, the area that were not considered or the error in our approximation becomes smaller. So therefore, first, we can conclude that there are more rectangles needed to cover the area. The approximation also becomes more accurate. This suggests that in order to get the exact area, the width must be as small as possible. So in calculus, it is possible for us to designate a particular expression that would relate into a very small measurement. Now, notice that from the past or from the previous slides, we have considered the width to be equal to x2 minus x1. And since we want it to be as small as possible, then approximately x2 minus x1 will be almost equal to 0, but not equal to 0. Now, therefore, we can say that from the concept of calculus, in particular differential calculus, such that any small difference, we can consider that as a differential of that particular variable, in this case, the differential of x. So a very small difference is defined as differential, as we all know. Now, for the height, as we can see, the height is measured from this particular point, which is the origin, up to the farthest length or farthest point on the element. So that will be considered as y. So the rectangular element or strip has dimensions y dx. Dx representing the width and y representing the height. So the area may be represented by, according to rectangle, that will be base times height or the width times height. That is simply y times dx. Now, if we would calculate the area of this strip with a very small thickness or width, then therefore we could say that that area is also very small. So thus, calling it to be the differential of area. And that is equal to y times dx. Now, since our task is to define or calculate the total area of the region, the total area is then equal to the summation of these small areas. So we are referring to the rectangular strip with a very small width. Okay, so summation in this case or in this context would mean integration. So therefore, we could say that the total area A is equal to the integral from A to B of those small areas represented by dA. Now, substituting the expression for dA, which is from the previous slide, y times dx, we have the following computation for the area. Now, we also know that in order for us to integrate in the dx world, or with respect to x variable, we must replace all the integrand in terms of x. Now, we know that this curve is represented by the function y is equal to f of x. So therefore, we can replace y by f of x, thus leading us to the equation or formula that we have introduced in the past. And that is the theory behind this particular formula. Now, as mentioned, we would be considering here regions bounded by multiple curves. Consider the following. Let's say we have two functions. Y1 is equal to f of x sub 1, represented by the blue curve, and y sub 2 is equal to f of x sub 2, represented by the green curve. So this is the region that we want to calculate for its area. So now we know that in order for us to calculate the area, we must represent that area with a particular rectangular element or rectangular strip with a very small thickness or width. So in this case, since this width is parallel to the x-axis, so therefore the computation of that is going to be x2 minus x1. And since we want it to be as small as possible, therefore we can say that that is the differential of x. Now, for the height, it's a little bit different than what we had in the previous slide. We should note that any y value or x value in the Cartesian coordinate system, they must be measured or referred from the origin. So for this particular point, which is sitting on the blue curve, we could say that the distance of that from the origin is y sub 1. For the green curve, it's going to be y sub 2. So therefore, the height is going to be the difference of y sub 2 minus y sub 1. Thus, the area of this small rectangular element is going to be, this is the base, dx, and this is the height, y2 minus y sub 1. Note that if y sub 1 is 0, we would be having the same equation as in the previous slide. In this case, however, y sub 1 is not equal to 0 because it has a particular curve representing the lower boundary of this element. So now, in order for us to calculate the total area, we would integrate or sum up all of these rectangular elements. So we get the integral of y sub 2 minus y sub 1 times dx. Now, for the limits, note that we must sum up we must cover up this region with those rectangular elements from this point up to this point. Now, also notice that those 2 points are the points of intersection of the two curves. So in this case, we must recall how to determine the points of intersection of those curves. However, considering that we have determined them ahead, let's say this point is at x is equal to 1, and this point is at x is equal to b. So therefore, the limits will be from the integral from a to b of y sub 2 minus y sub 1 times dx. Now, personally, I would like to write this equation in this manner. That is the integral from the lower limit to the upper limit b of y sub u. So y sub u represents the upper curve minus y sub l. Y sub l represents the lower curve. So again, y sub u represents the upper curve and y sub l represents the lower curve. So in this particular case, as we can see, y sub 2 represents the upper curve and y sub 1 represents the lower curve. So this is just a matter of generalizing the formula that we have to use. Now, what if we have the following curves that would bound our plane region? So now, if we are attempting to find the area of this, so we might be thinking that we could use a rectangular strip in this orientation. However, it is important that we must consider the fact that there should be consistent upper and lower bound of a particular strip. So for this example, since we are considering a vertical strip or vertical rectangular element, it should be important to note that the lower end and the upper end should have a consistent type of curve. Now notice that as I run this curve towards to the right, we can see that the upper boundary or the upper curve changes from the blue curve to the green curve. And therefore, there is an inconsistency with the upper bound of the curve. If this is the case, then we will need to subdivide the area before we calculate the total area, which is impractical and inconvenient. That's why there is another option. Instead of using a vertical rectangular element, we can also choose to use a horizontal rectangular element. Wherein, if we consider rectangular element in this case, as you can see, we will just need to note that the left and the right end of the element would have a consistent type of curve. So the rectangular elements will run from this point to this point. So as we can imagine, the left end will always be represented by the blue curve and the right end will always be represented by the green curve. Okay, so now let's define the width. In this case, the width is finite. It is actually measurable, and that would be x2 minus x1. The side that is unmeasurable or infinitesimal is going to be the height, because we need this to be as thin as possible. So therefore, the dimension there would be y2 minus y1 almost equal to 0. So therefore, that would be represented by the differential in y. So applying the same concept, we have the base times the height. Integrating or summing up, we have this equation. And then we have to consider these points as our limits. Take note that because we are now integrating with respect to y, our limits should be in terms of y as well. So in calculating these points of intersection, what we need in those coordinates are the y coordinates. So we have here y is equal to a for the lower limit and y is equal to b for the upper limit. Thus, making this equation our general equation for the computation of plane region in this particular case. Now, like I did in the previous case, I like to write this equation in this manner. The integral from the lower limit a to upper limit b of x sub r minus x sub l times dy. In this case, x sub r represents the right curve. X sub L represents the left curve. So in this case, the right curve is represented by the green curve, which is y sub 2, and the left curve is represented by the blue curve, which is y sub 1. Okay? Now let's have an example. For this example, we are asked to calculate the area between f of x and g of x, where f of x is represented by 3x minus x squared and g of x is equal to x. The first thing that we need to do in order for us to calculate the area of the region is to graph these curves. It would be impossible for us to determine the correct orientation of the required rectangular element if we will not draw the curve. So here we will use what we have learned in pre-calculus or in analytic geometry. So first, consider the graph of f of x equals 3x minus x squared. We should recognize right away that this is a parabolic curve. And this should be written in this way. So yung f of x, I just replace it by y. So from here, we just need to rewrite this on the standard form of the equation of parabola. So what we do first is we apply completing the square. And then we express the perfect square trinomial as a square of binomial, as shown here. And then the standard form of parabola requires that whatever coefficient in y should be factored out. In this case, -1. So from this particular equation, this is already in standard form parabolic equation. So this means that the parabola has a vertical axis opening downwards with vertex at 3/2 and 9/4. 9/2. This should be 9/4. Sorry for the mistake. No, should be 9/4. Anyway, from the graph, if we plot that in our Cartesian plane, so this would be the drawing. So this would be the point 3/2, 9/4. Next is to determine the graph of the second curve. And the second curve is actually a line. So the graph of g of x is a line passing through the origin. So this is going to be the graph of that particular line. So therefore, the region that we need to find the area is this particular region. So now we calculate the point of intersection because the point of intersection will tell us the upper and lower limit. So there, take note or recall that the point of intersection will be represented by the boundary of the plane region they enclose as mentioned. So how do we calculate the point of intersection? So note that the coordinates of points of intersection are the algebraic solutions of the simultaneous equations of the curve. Or to put it simply, to determine the point of intersection of these two equations, all we have to do is to solve those two equations. So this is our equation 1 for f of x. This is our equation 2 for g of x. Solving them simultaneously, in this case, I use substitution method. And then since this is a quadratic equation, we will be able to calculate two possible roots for x. So when that is x is equal to 0 and x is equal to 2. And in the graph, this is going to be the point where x is equal to 0. And this is going to be the point where x is equal to 2. Now, we will choose our rectangular element orientation. So as we know, we have two options. We can use vertical or horizontal element. Just making sure that the ends would have consistent curve. In this particular case, it is much better to use a vertical element because if we use a vertical element, the top end would always be represented by the parabola and the lower end would always be represented by the line. So therefore, it is consistent. So it is applicable. Now define the dimension. So we know that the dimension of this height is y upper minus y lower. And the width is going to be dx. So the area may be represented as discussed previously. So the upper curve is represented by the parabola and the lower curve is represented by the line. So the limits will be from 0 to 2. So applying that in the equation, so we can now integrate. So integrating, so this is going to be integral by power for each of them. So this is going to be x squared. And the second term will be x cubed over 3. So apply the limits. So for the upper limit, we substitute to the antiderivative. And then the lower limit, we do the same thing. And then we just subtract them. Therefore, the area of that particular region is equal to 4/3. Now let's have another example. This time, we are asked to calculate the area bounded by the curve y squared minus 2y is equal to x and x minus y plus 1 is equal to 0. So similar to previous example, we just need to graph the curves and determine their points of intersection. So the graph of this is going to be parabolic and the graph of this is going to be a line. So as shown here. So this is the line and this is the parabola. In order for us to determine the point of intersection, we just apply a method of substitution. So from the first equation, we solve for x. Y is equal y that is equal to y minus 1. And then from the second equation, which is y squared minus 2y equals x, we can replace x by y minus 1. And from here, we can solve for the values of y. Now, the reason we solve for the values of y instead of x is because we are going to use a horizontal rectangular element for this particular computation of area. as we can see, if we use a vertical element, it won't be consistent at this particular region, or the upper and the lower boundaries are not consistent at the lower boundary for this position and this position. So thus, we use horizontal rectangular element with dimension x right minus x left for the width, and the height is dy. So therefore, the area may be represented as the integral from a to b of x right minus x left times dy. So the right curve is represented by the line, while the left curve is represented by the parabola. So we just substitute them. And also the limits are already calculated previously. So therefore, the area may be represented as follows. So we can simplify first before integrating. So notice that this is y, or should I say this is negative y squared, but this is y minus negative 2y, giving us positive 3y, and then this negative 1 retains. So this is just integrable by power, so that is going to be the antiderivative, and then we just apply the upper and the lower limit. And that is going to be the area.